Hi students, today we're looking at limits as they uh, kind of mix with what we've talked about in previous classes as far as continuity. We're going to extend our definition of continuity to include calculus based on what we're learning so far this year. As always, on your copy you're going to have some stuff here that are specific Khan Academy assignments that you can use to check your understanding. All right. We got all kinds of fun things going on as we warm up into this. The first thing we're going to take a look at is this weird rational function, and we're going to try to figure some stuff out about it. Then we're going to look at a piecewise function and do the same thing. What I'd like you to do is to spend a couple minutes trying this on your own if you have not already, and then kind of join us again and see what happens. All right, first thing I see here, I see that there's factorable stuff. I'm a big fan of factoring things when I see them in rational functions. I know I can take a 4 out of that. In fact, I can take a 4x out of that, end up with an x minus 1. And then in the bottom, that's difference of squares, so we get x minus 1 and x plus 1. All right, hopefully your training from Algebra 2 holds well, and you're going to say before we do any canceling that x cannot equal 1. X cannot equal negative 1 because that would make those 0. And when we take a look at this, now when we cross those things out, that doesn't mean that x can start equaling 1 again. It means that we have a hole in our graph when x equals 1. All right, and then we're left with the graph of 4x over x plus 1. If I were to kind of sketch this out, I'm going to have an asymptote at negative 1. I know I'm going to have a hole at x equals 1. I don't really know where that's going to be, so I'm going to put some dots there. Based on my ratio of coefficients, my horizontal asymptote is going to be at 4. And if I plug 0 in, I get 0 over something, so we'd end up at 0 at 0. To me, that suggests that my graph is going to look something like this with a nice hole there, and then something like this. Okay, talking about continuity here. I've got two places of discontinuity. The first place I have discontinuity is about this asymptote. So at negative 1, we have an infinite discontinuity. And I can see that because my graph literally has an asymptote in the middle. In terms of limits, my limits as I approach both sides of that asymptote can't possibly equal the same thing. All right, the other thing I've got going on here is I've got a hole in this graph. Coming from both sides, the limit's okay, but this time that point is not okay. Okay, looking at my piecewise thing, here I've got x is 2 is my breaking point, negative 2x plus 6. It's going to be something like this. And then going down, I love it. Beautiful. Nice open circle there. And then x squared minus 1, so we'd be at negative 1, kind of going up. At 2, we'd be at 3, and at 2 on the other one, we'd be at 2. Cool. And continue like a parabola does. All right, talking about the continuity here, we've got a jump discontinuity. The limit from both sides is not the same, so that's pretty clear that we have some limit stuff going on, we've got some continuity stuff going on, and that's about all we can take a look at from there. So we end up with this idea of continuity that's being kind of loosely formed here. Some of the things that we said for something to be continuous at a point, should be continuous about a point, but I was running out of room. A couple things have to be true based on these things here. The first is that the limits have to exist. The limit as x approaches a from the right of that function, whatever it is, must equal the limit as x approaches a from the left of f of x. We've talked about this before. This is the first thing that we kind of showed that you could do, which is that the limit exists. And now we are adding to that if the limit exists, then we can think about continuity. But we also looked at this guy, and here we said that the limit exists. However, this graph is still not continuous. We have a hole in the graph. So not only does the limit need to exist, so I'm going to say I don't even know why I said that. The limit as x approaches a, I'm going to make this slightly neater by erasing my scribbling, of f of x must also equal the value of the function at that point. In other words, if I were to plug in a, I have to get the same value. For my first example, we get nothing. That point doesn't exist. In my second example, we'd end up getting that top point, although that breaks that first part, so that doesn't even apply for this. This two kind of step process is going to be the key to everything that we do here for the rest of this activity. Okay, here we're told the function is continuous everywhere except x equals -3. What value would make that true? Okay, well, I know that the limit from both sides has to be the same. I've got the same function from both sides, so I'm hoping that's going to be the case. And then I also know that f of 3 must equal c. Okay. So that's what's going on here. This top part, that's my limit finding function, because that's both sides, but not actually the actual place. That gives me some insight. Okay, so the limit as x approaches 3 of 2x minus 6 over x squared minus 9. That's going to be the limit as x approaches 3 of 2 times x minus 3 over x minus 3, x plus 3. By the way, I'm doing this because I made a mistake the first time on this problem, and before I started doing the math, I found it to be 0 over 0, which I did not show here. So I can only really use this because I know that we get 0 over 0 here, so it's indeterminate. Factoring looks possible. When we do that, we end up getting 2 on top, and if I'm plugging 3 in, I've got 6 on the bottom. That's the limit. That must also equal the function value at that point. Therefore, c must equal 2/6. All right, for the bottom one, here we've got two different possible breaks in the gap. We've got at x equals 0, and then we've got at x equals 2. To be continuous, we need two different things happening. We need the limits from the left and the right to be equal. So at each place, I'll do 0 first. As x approaches 0 from the left, that's my left side, 2x minus 3a. And the limit as x approaches 0 from the right, okay, that's my right side, ax squared plus 2b. Those must be equal. Plugging 0 in, we've got negative 3a. Plugging 0 in, we've got 2b. Nice. I'll solve for, I like they wrote a instead of b. I'll solve for a just to get rid of that negative for no real reason. And we've got a is equal to negative 2/3 b. Not helpful on the outset because I need a and b to make this work. Okay, let's try at our other breaking point. So now we're talking about the limit as x approaches 2 from the left of ax squared plus b, plus 2b. And that must equal the limit as x approaches 2 from the right of x minus 4. All right, plugging 2 in, we've got 4a plus 2b. And on the other side, plugging 2 in, we get negative 2. Hey, we've got a system of equations here. We've already solved for part of this. So we might as well plug this in. 4 times negative 2/3 is going to be negative 8/3 b. plus 2b is equal to negative 2. That's going to end up being negative 2b is equal to negative 6. When I divide, I get b is equal to 3. Plugging that in, that's going to net me a is equal to negative 2. Those are the values based on finding the limits from both sides at both places that would make this continuous. All right, next up we've got a value of k. Here we've got to, again, start from the limits. The limit as x approaches 2 from the left, that's my top one, of kx squared is going to be equal to 4k. And on the bottom, my limit as x approaches 2 from the right, yep, that's definitely the bottom one, kx minus 6, and that's going to be 2k minus 6. Knowing that those two must be equal, we end up with 4k is equal to 2k minus 6. That gives me k is equal to negative 3. Same thing down below. Now we're splitting it 1. So the limit as x approaches 1 from the left, that's my top part, of k squared minus 12x. That's going to give us k squared minus 12 when I plug 1 in. And then on the bottom, the limit as x approaches 1 from the right of kx is going to be k. Setting those equal to each other, k squared minus 12 is equal to x. Going to move that x onto this side, move that k onto this side, and set that equal to 0. That's going to give us k minus 4, and k plus 3 is equal to 0. K equals 4, and k equals negative 3. Those are two different values of k, both of which fit that equation. All right, just plugging those guys in to make sure. We've got 16 minus 12 times 1 is going to be 4, and 4 times 1 is going to be 4. Cool, that works. How about negative 3? 9 minus 12 times 1, negative 3, and 1 times negative 3 is negative 3. Both of those work. We are beautiful.